You learned in my class, the last class that you were here, that matter is made of atoms. And atoms at the same time they're made of subatomic particles. And what are the subatomic particles? Do you remember them? No, Miss Rama, we don't care. We're not going to talk to you. This is my nucleus. In the nucleus of the atom, you're going to find there protons that are positive and neutrons that are neutral. If the number of protons is giving you what? The atomic number. Yes or no? Now, floating here in the cloud, we have the electrons. Electrons, the charge is negative. So, for example, let's say that you have over here 11 protons because you're talking about a sodium atom. Since the atom is neutral, you're going to have 11 electrons floating in the cloud. Questions about that? You don't have any questions about that? Okay. I'm going to continue. You learn about isotopes. And what are isotopes? They don't want to talk to me. And some of them, they want to be doctors. Imagine. They use a lot of...
Isotopes are, okay, so an isotope is an atom of the same element, but it has a different number of those protons, right?
Can that be possible? Remember that the number of proton is the atomic number, and the atomic number is the social security number of the element. You change the number of proton, you have a new element. Okay? See that? Is, okay, isotopes, they are atoms of the same element. So what do they have in common? They have the same number of protons. Do they have the same number of neutrons? And I was talking about isotope notation. Okay, by the way, no, it's not like that. A genuity is calling that nuclide or nuclide. I don't know how to pronounce that. Is calling that notation nuclide. For me, this is an isotope notation. Isotope notation. And why an isotope notation? Because remember, the number over here is going to give me the number of protons. And this number here is giving what? The mass number. How do you calculate the mass number? Silent treatment. They don't want to talk to you because they don't like you. Okay, so you have that in another video. Knowing how to calculate the mass number. A mass number is the number of protons. Who's giving you the number of protons? The atomic number plus the number of neutrons. If you have over here the atomic number, which is the number of protons, and the mass number is equal to 14, how many neutrons do I have in this isotope of carbon? How many do I have?
8.
You have 8. Okay? Now, in a regular carbon atom, in the nucleus, you're going to have 6 protons, which are positive. In the cloud, you're going to have 6 electrons, which are the negative. And you're going to have 6 neutrons. See? When the mass number is equal to twice the atomic number. Okay, let me raise this over here. The atomic number, you have a stable isotope. Miramos, over here we don't have a stable isotope. What's gonna happen? I wanna let you, I'm gonna teach you the next class. Right now, I'm going to concentrate on binding energy and mass defect because you have a homework waiting for you in Google Classroom in which you have to calculate that. All the element. Questions about that? You don't have any questions about that? Okay. So you have a problem over here. Tritium is an isotope of hydrogen. And over here, you have what they call in ingenuity a nuclide, and I call isotope notation. Karim, this is my isotope location. Isotope notation. How many protons do I have in that atom? In this one, Karim. How many do I have? How many protons? Huh?
3.
Do you agree with that, Christian? How many protons do I have? They don't want to pay attention to me. And I was explaining that in the slide before.
Yeah.
That number over
That's
here.
one proton.
One proton. If that number over here is representing what? That 3 over there is representing what?
The neutron.
The mass number. So in this specific atom, how many neutrons do I have in the nucleus?
2.
2. Okay. Understand that part? Understand how from the isotope or nuclide, because ingenuity is calling that nuclide, from the isotope notation or nuclide, you can like get amount of protons and amount of neutrons. Okay. I'm gonna continue because I'm gonna solve the first problem. If you know that in my class we have a routine. Every time that we're solving a problem involving math, we're gonna start with the list. Number of protons, 1. Number of neutrons, 2. And we know why, right? Do I have to show that over there? No, maybe. Okay, you're not talking to me. Okay, good. You know what I'm gonna do? I'm gonna do this step by step. Since I'm recording all of this, I'm going to do this step by step, and you have to complete that my way. You don't complete that my way, I'm not gonna give you credit. So this is my isotope notation. So number of protons equals 1. Mass number equal 3. Mass of proton. What do I have that over there? Is 1.0078, 1.007825. I'm on. Okay. 7825. Mass of a neutron. Let me erase this over here because it's not that the proton is from one proton. The mass of one proton. Mass of the neutron is 1.00A. Okay. 8665 atomic mass units. Okay. And I'm gonna give you these 2 conversion factors. Okay? These 2 conversion factors. 1 atomic mass unit is equal to 1.66054 times 10 to the negative 27 kilograms. I'm gonna give you that. And 1 megavolt is equal to 1.6021. It's a big number. Big number, no, it's super small. Joules. Okay, so that's a given. Always is gonna be a given. Okay, miramos, one that you have that, how are you gonna find the mass defect? Okay, my second step. Formula. And I know that the mass defect is equal to the mass of the isotope minus the average atomic mass. que, by the way, in problem number 1 is also a given. Okay, so it's 3, the average atomic mass, 3 point, a ver, 0160, 0160 490 AMU. Okay, so it's another given, the average atomic mass. Ms. Ramos, how are we gonna find the mass of the isotope? Mass of the isotope is the number of proton multiplied by the mass of the proton plus the number of neutrons by the mass of the neutrons. And that's my first step. That's what I'm going to do. I know that I have only one proton and the mass of the proton is 1.007825. And I know that I have 2 neutrons. Y why 2 neutrons, Ms. Ramos? Because mass numbered is number of proton plus number of neutrons. The mass number is equal to 3 number of protons. See that? When you isolate the X, then you have a 2. It does the 2 that goes in the number of protons, in the number of neutrons. See? Knowing the mass number and the atomic number of the element, because it's the number of protons, you can find the number of neutrons in that specific isotope. So with that information, esta gente no van a parar de mandar email. My goodness, I don't know what they imagine that we're doing here in the class. Okay, so you're gonna multiply that by 1.00 AMU. And once that you have that, okay, so let me put that over here. Mass defect. Okay, let me use my calculator. See, I multiplied 2 by that number, then I was adding this number, and this is the mass of my isotope. The mass of tritium, which is the name that you receive when you have an atom of hydrogen that has how many extra neutrons? How many extra neutrons do I have in tritium? If this is the isotope notation, you're gonna learn like chemistry, the same way that I'm learning about aliens. Okay, whatever. I'm just making this so you can play this later. If you have this isotope notation, how many extra neutrons do I have in the nucleus? Okay. Mass defect. Okay, so the mass of the isotope, 55 AMU minus 3.0160, 490 AMU. Ms. Ramos, what is this number coming from? It was a given in the problem. So I'm gonna subtract that, 3.0160, 490, and the mass defect is equal to 0.006 amount of mass unit. Questions about how to find the mass defect. Can I have a mass defect that is negative? Can I have a mass defect? Impossible. You're not paying attention, and I'm putting my life on this. Okay, but I'm not done. So that's the mass defect. You remember the mass defect can never be negative, because that means that you have minus 0 mass. Like, it's impossible. And in addition to that, you know that the mass defect is the difference between the mass of the given isotope minus the average atomic mass of that element. And when you have an isotope, always is gonna be, the mass of the isotope is gonna be smaller than the average atomic mass of the element. Always, because remember that the average atomic mass is affected by the different isotopes. Isotopes that can be heavier or lighter, depending, but always has to be, the mass defect always gonna be positive. Now, in addition to the mass defect, what else do you have to find in this problem? The binding energy. Ms. Ramos, what is the binding energy? And you have the definition here. Is the nuclear energy required to split a nucleus of an atom into its component parts, into protons and neutrons. How you gonna calculate the binding energy? Okay, energy, according to Einstein, is equal to the mass multiplied by the speed of the light squared. Mirame, what is the speed of the light? Do you know what is the speed of the light? Any of you in there? No? The speed of the light? No, and you don't care. 3.00 times 10 to what power? Let me see, I don't remember. 28? I don't remember. They're not paying attention to me. I want you just to stay record that they're not paying attention. One of them, they're on the cell phone. The other one, I play, say what, I don't know what, and whatever. It is what it is. This is what we have right now. Okay, speed of the light. If I open the homework assignment and it's not done the same way that I'm doing it here right now, they're not getting credit. A speed of light is 1, 2, 3, 4, 5, 6, 7, 8. 10 meters per second. That's the speed of light. Ms. Ramos, the mass is coming from where? The mass is coming from the mass defect expressed in kilograms. That's why you have this conversion factor over here. You have that conversion factor over here. So you have to express the mass defect in kilograms in order to put that over there. The mass defect is equal to 0.009106 AMU. You're going to multiply by the conversion factor. 1 AMU. All of that was done in ingenuity. I don't know, I don't really know what I'm doing this. But I'm doing this anyway. 1 MMU, 1.66054 times 10 to the. You're going to cancel amount of mass unit, and when you multiply 0.009106 times 1.66054, that is gonna be equal to 0.12088 times 10 to the negative 27 kilograms. Times 10 to the negative 27. I don't like this number. Why you don't like this number? Because I don't like decimals that has zeros in front. So I'm going to move my decimal. 1 and 2. Yes. What happened? What happened? Okay. I don't know if you understood what I did, but I was teaching you how to do that at the beginning of the school year. So I did that. Okay, writing that in scientific notation. Now that I have the mass in scientific notation, I'm ready to calculate my binding energy, because I have the mass in kilograms, which is 1.51208 times 10 to the negative 29 kilograms multiplied by 3.00, okay, by the way, I have only 3 significant figures here, times to the 8 meters per second. And when I'm multiplying kilograms by meters per second, the unit that I'm going to have at the end, joules. And that's why you need to have the mass over there in kilograms. So I'm going to multiply my mass. My mass. Times 3. 4 point, only 3 significant figures in here. 54 times 10 to the negative 21 joules. Questions? Questions? You don't have any questions. So you know where the negative 21 is coming from. Love that part. Okay, you know how here I went from negative 27 to negative 29. Okay, I love that. I love that you know how to do this. So going back to my problem. So I have to answer. Oh my goodness, I was erasing everything. Okay. I have to answer the question in complete sentence. No. No. Mass defect of the isotope. And you can write that in kilograms, or you can write that in amount of mass unit. It doesn't matter. 0.009106 AMU. The binding energy is, a ver, 4.54, no, 24. 54. 4.54. Is 4.54 times 10 to the negative 21 joules. Questions? No questions? Okay. Load.